You've probably heard that quantum computers will cure cancer, break the internet, solve climate change, and perhaps one day even fold your laundry. But is any of that even true? Some of it is definitely complete nonsense. In this fourth and final lesson of Use a Quantum Computer today, we are going to go over quantum computing applications, separating hype from reality, so that you can better navigate the sometimes clickbaity press releases, headlines, and conversations around quantum computing going on today. You previously learned how to program your first quantum circuit and a little bit about the math behind gates and how quantum states work. But now I'm going to cover some general knowledge that anyone working in or tangentially to the field should know. But first, let's go over what a quantum computer is and what it isn't. Quantum computers are not faster laptops, not magic, and not replacing classical computers anytime soon. They are specialized machines and very good at specific computational problems. But if your problem is in Excel, email, or Minecraft, quantum is not your guy. And stop asking me if my quantum computer can run the video game Doom. It can't, and it won't. But there are some real meaningful applications of quantum computing. Let's go over those. The golden child of quantum computing research is simulation of chemistry and nature. Much of the time, when you are trying to simulate things on an atomic level, classical computers are going to struggle, and at some point as the problem size grows, they will inevitably fail. This is because classical computers cannot intrinsically mimic quantum mechanical interactions that they have no real awareness of. But quantum computers can. They are very familiar with quantum mechanical interactions because they run on them. So with these types of tasks, we're basically asking quantum computers to do some self-reflection. And this will have effects outside the research lab and for people besides just scientists as well. Think of things like battery research, materials, drug discovery. These are things that would have real impacts for everyone. But I will caution that this is not as simple as pressing a button and discovering new medicine. It's more like run a smarter experimental loop. We still have a lot of work to do in this area before it becomes ubiquitous, but it's coming. Another application area, which might be a little further out than simulation, is optimization. Think scheduling, routing, logistics, even in finance. We think some problems might see computational quantum advantage. But keep in mind, many optimization problems already have excellent classical solutions. Quantum would have to be really good to beat those algorithms. Quantum computing offers alternative approaches by cleverly framing optimization problems as energy landscapes, where the goal is to find a lowest energy configuration. Sound familiar? We did that in episode 3. The lowest energy configuration translates to the most optimal solution. And while it's still an open question when, or for which problems, quantum optimization will deliver clear advantage over state-of-the-art classical methods, optimization remains a major area of interest due to its ubiquity and the natural mapping between optimization objectives and quantum Hamiltonians. Another area of application is solving something called partial differential equations, PDEs. PDEs describe heat flow, fluid dynamics, electromagnetism, waves, diffusion, and more. Basically, if something spreads, flows, vibrates, or evolves over time, it's probably a PDE. And if you're a researcher of any kind and you've ever wondered, why is my simulation running so slowly? Congrats, also probably a PDE. But why are these equations so hard to solve with classical computers? Well, part of the problem is space. The real world is continuous. But when we model something, we need to discretize it into smaller chunks, but a lot of them, which leads to really huge mathematical matrices. There is a lot of accuracy versus compute cost trade-offs. Every time you refine the mesh or the number of simulation steps, a GPU fan somewhere spins louder and angrier. Quantum computers might be able to offer potential advantages for systems that can be rewritten into linear systems, with certain scaling improvements and high dimensional problems that could be cast into lower dimensions. Basically, they could, with specific mathematical subroutines inside PDE solvers, make the problem more efficient. And lastly, we have quantum machine learning. This is probably the most controversial possible application area, and there are a lot of caveats. Quantum machine learning does not equal a magical AI upgrade. There's still a lot to be learned in this area, but we are optimistic that there could be speedups in very specific subroutines. For instance, in near-term algorithms, quantum kernels might provide advantages over classical ones for certain datasets. In the fault-tolerant regime in the future, we can expect quantum computers to perform certain linear algebra operations useful for machine learning with speedups. However, if someone tells you that quantum AI is about to replace your favorite LLM, they're selling you something, and you shouldn't buy it. It's also important to understand the direction the field is heading in terms of benchmarks. Qubit count is not the only important metric that we care about. Just as important are quality and speed. Without good quality qubits and fast gates, the total qubit number just doesn't tell the full story. It's important to keep track of how all three are progressing. So in conclusion, I hope this lesson has made it clear that quantum advantage isn't about replacing computers. It's about expanding what is computable. It is one of the most ambitious engineering projects that humans have ever attempted. And like all ambitious projects, it's messy, slow, but actually quite amazing. If you want to follow up on how these algorithms actually work, hit subscribe and check out my other series, Quantum Computing in Practice, or follow this introductory learning path. Or, if you want me to roast quantum hype headlines once a month, let me know in the comments below. We'll see you next time.